let's consider a rational function where the denominator is 1 degree higher than the numerator, and we want to attempt to sketch this function. And to sketch this function, we're going to follow the same strategy that we've been looking at regarding other rational functions, right? So this includes looking for the domain, the range, the intercepts, and so forth, right? And the asymptotes. Now, one thing you have to note that if you have a function f of x is equal to a xn plus c, and the denominator is 1 degree higher, xn plus 1 plus d, right? The horizontal asymptote y is always going to be equal to 0. Okay, so the horizontal asymptote will always be equal to 0, and in this case, we need to, so just off the bat, as long as there is no vertical shift, right? If there is a vertical shift plus e, then the horizontal asymptote is going to be plus e. Okay, so that's the idea regarding that. Beyond that, there is no slant asymptote or no oblique asymptote, right? So there's no oblique asymptote or slant asymptote, whatever you want to call it. And we look at the vertical asymptotes the same way by looking at the restrictions on the domain. So there's nothing too difficult here. However, there are a few exceptions when we're looking at rational functions where the degree is 1 higher. Now, in some cases, the rational function will actually cross the rational function will actually cross the x-axis. So that's where we're going to see a few anomalies, right? So these are a few exceptions, but the restrictions here are that, well, instead of calling them restrictions, the exceptions here is that we said that the horizontal asymptote exists where y is equal to 0, but the exceptions are that x-intercepts may still occur. Okay, so x-intercepts may still occur even when the horizontal asymptote y is equal to 0. So this is where the exceptions will come in. So that's why these ones are, I wanted to kind of separate these versus the other rational functions. And as we look at more and more complex rational functions, where the degree and the degree of the numerator will approach, like, or the denominator will approach cubes and so forth, it gets really difficult to kind of pinpoint general ways to sketch them, right? So for the most part, we need to kind of consider that the exceptions do exist for these type of functions. So let's take a look at how we can sketch this, right? So in this case, the first thing I want to do here is I'm going to look at the domain. Okay, now to find the domain, I'm going to just simplify this function. K of x here is equal to x minus 3. If I factor the denominator, this is actually a perfect square trinomial, and you can factor it as x plus 3 squared. Okay, so looking at that, so this is the function that I'm going to be working with, my simplified function. The domain here, x belongs to all real numbers, but x cannot equal -3. Okay, the range here, because of that, y belongs to all real numbers, and because the degree of the numerator is 1 higher than the denominator, then we're going to say that y cannot equal 0, right? So we know that the restriction on the domain here is the vertical asymptote. So the vertical asymptote occurs at x is equal to -3, and the horizontal asymptote occurs when y is equal to 0. So that's the idea. Now, remember how we said that there is an exception here? Even when the horizontal asymptote y is equal to 0, this implies that the function won't cross the x-axis. However, we do have an x-intercept, and the x-intercept is discovered by solving for the numerator. So if I wanted to find the x-intercept, this is where the exception kind of comes in, where I let k of x equals 0, and therefore x minus 3 is equal to 0. So 3 and 0 is an x-intercept. So the graph actually will cross the x-axis at 3 and 0. So we're going to investigate this when we actually sketch the function out, right? Now in the other scenario, we can also solve for the y-intercept. So if we're solving for a y-intercept, we know that I'm going to let x equal 0. So k of 0 here is 0 minus 3, 0 squared plus 6 times 0 plus 9, so you're going to get -1/3. So you're going to get 0 and -1/3. So this is basically your y-intercept. Alright, so now we have our vertical asymptote, our horizontal asymptote, our intercepts. Let's create a sketch here. Right, so I'm going to implement a grid. Alright, so here's my grid, and what I'm going to do here is I'm going to plot my vertical asymptote. Let's do that in red, so -3. Alright, so let's say that's somewhere here. So you're going to, guys, use a ruler for this. Whoops. See, it's just kind of hard to, it's going to take my time here. There you go. Okay, so this is my vertical asymptote. X is equal to -3. And we also have a horizontal asymptote. I'm going to do that in lime green. And that's basically the x-axis. So this is my horizontal asymptote. Okay, so that's my horizontal asymptote. X is equal to 0. So based on this premise, I'm sorry, x is equal to 0, y is equal to 0. Sorry about that. So y is equal to 0. So based on this premise, the function shouldn't cross the x-axis. However, we do have an x-intercept. So that's where you're going to see it actually cross over, and there's going to be a crossover here. So there's going to be a 3 and a 0 here, right? And beyond that, we also have a y-intercept of 0 and -1/3. So let's say that it's somewhere here. So this is 0 and -1/3. So based on that idea, right, one of our graphs here is basically going to look like this. I'll do the graph in blue. One of our graphs is actually going to look like this, right? Across the y-intercept, and then it'll cross through the x-intercept, and you guys can do a series of test points, right? You can plug in some functions, and you'll actually find that the function will be really close to the horizontal asymptote. Now it's going to actually approach the horizontal asymptote from up top, right? So that's essentially what's happening. Like, it basically goes through and then it approaches the horizontal asymptote from the top. The other graph here you can figure out by using test points, right? So this is a vertical asymptote. What I'm going to do here is I'm going to do f of, well, in this case it's k, right? K of, let's do -4, for instance, right? So -4 is going to give us -4 minus 3. So this is where the test points will actually kind of help us to figure out this function. -7/1, so this is going to give us -7. So -4 and -7, which would look kind of like, this is -4, -7 looks like that, right? So you can see that, you know, the graph is going to basically follow something like that. And if you actually draw test points here, this one will follow the confines of the asymptote, right? And you can actually show that the values beyond the x-intercept are above the horizontal asymptote. Like if I plug in x of 7, for instance, right, you get 7 minus 3 over 7 plus 3 squared, and you get 4 over 4 over 10 squared, right, and you get basically 4 over 100, right? So it's like 0.04. It gets really close to this horizontal asymptote. So that's where the exception kind of lies in, and we can basically also look at our end behaviors. So I'm just gonna maybe use a different color, something darker. And my end behaviors here, so if I look at my end behaviors, as x approaches -infinity, right, so as I go this way, right, to -infinity, we can see that f of x or y will approach 0 from below. As x approaches, let's say we're approaching the vertical asymptote, -3 from the left side, y will approach -infinity. Okay, so these ones are actually, this is where the exception does occur, but we can still somewhat sketch it, right? But beyond this, when we have cubes and so forth, more complex rational functions will give us a lot of trouble. Really, calculus is used to sketch functions, so we're somewhat limited in the patterns for advanced functions for this course anyways, right? So x approaches -3 from the right side. If we approach the vertical asymptote from the right here, you can see that the function also approaches -infinity, and as x approaches positive infinity, as it crosses the x-intercept, you can see that y will approach 0 from above. Okay, so this is very important to kind of understand the end behaviors, but this is what the sketch looks like. So just make sure that you guys remember that there is an exception here, and that although you have a horizontal asymptote of y is equal to 0, you can still have x-intercepts that